Hi, so today I would like to take an example given by a physicist and a mathematician in one of his books called The Elegant Universe. The example goes like this. There are two countries that have gone to war and they've been in war for a long time. But later the two countries decide to sign a peace treaty. The names of the two countries are Forward Land and Backward Land. But however, the situation was such that none of the presidents of both the countries wanted to sign the peace treaty first. So there was a need for a certain arrangement so that both the presidents signed the treaty at the same time. The UN Secretary General comes up with a solution, and the solution was that both the presidents would sit on a table and they would be opposite to each other, and there would be a bulb in the middle of the table, and as soon as the bulb is switched on, both the presidents would have to sign the peace treaty. This ensures that both the presidents sign the peace treaty simultaneously. The UN Secretary General also proposes that both the president sign the treaty on a train. The table would be on a train, and both the presidents would sign the treaty based on the proposed arrangement. The UN Secretary General proposed a train because he wanted that the presidents sign the peace treaty simultaneously while they were being watched by the people of both the countries who would be on either side of the track on which the train was moving. Both the presidents of the Forward Land and the Backward Land agree to the proposal given by the UN Secretary General, and they decide to go ahead with the signing of the peace treaty. So here's a train, and there is a table in the train. On the opposite sides of the table, both the presidents sit, and in the middle of the table is a bulb. There are also other officials in the train belonging to both the presidents. There is also the Secretary of UN General Assembly. The train starts running and the people are on either side of the track. The Secretary of the UN General Assembly switches on the bulb, and the presidents of both the backward and the forward land sign the peace treaty. But it's not as simple as that. The people of the backward land complained that the president of the forward land had signed the peace treaty before the president of the backward land. However, there are no such complaints from the officials who were in the train. So they observed that both the presidents had signed the treaty simultaneously. Now the big question is, which group of people are right? Is it the group of people that observed that the president of the backward land signed the treaty later than the president of the forward land? Or is it the group of people who were in the train and observed that both the presidents signed the treaty simultaneously? Who is right? And the answer is, both of them are right. Well, that's a strange answer, but that is the truth. This is a situation where there are two groups of people. There are people on either side of the track. They are observers at rest, and they were observing an event that was in motion because the train was moving. And there is another group of observers who are in the train, the officials belonging to the presidents of either countries. The velocity of the train with respect to these officials is zero. Whereas this is not the case for the group of people who are outside the train on either side of the track, observing that the train is moving. There is a velocity of the train with respect to these group of people. And as the train keeps moving, at one point the UN Secretary General switches on the bulb, and there's a light beam coming from the bulb, and the light beam travels towards the president of the backward land. But at the same time, when the light is in transit, the president of the backward land is moving. He is moving away from the light beam. When it comes to the president of the forward land, the light beam is moving towards him, but the president of the forward land is moving towards the light beam. So in effect, what is happening is the president of the forward land is meeting the light beam earlier than the president of the backward land. Now all this is with respect to the people who are outside the train, who are observing the train is moving, but not with respect to the people inside the train, the officials of either of the presidents. Since the light beam takes a little bit longer to reach the eyeball of the president of the backward land, as the president of the backward land is moving away from the light beam, the people who are observing this event of switching on the light and presidents signing the peace treaty from outside the train observe that the president of the backward land had signed the treaty later than the president of the forward land. The eyeball of the president of the forward land is able to meet the beam of light earlier than the eyeball of the president of the backward land does. The fact that the light takes more time to reach the eyeball of the president of the backward land than it does to reach that of the president of the forward land can also be proven mathematically. And the max goes like this. Imagine the distance between the two presidents, which is the length of the table, is d. Since the bulb is in the middle of the table, and here we are interested in finding out the distance the light beam travels to reach the eyeballs of either of the presidents. The distance the light beam would have to travel to reach the eyeball of the president of the backward land would be more than the distance it would take for it to reach the eyeball of the president of the forward land. So here we'll come up with the equations of both the distances. Let us take the section of the light beam that has moved to the president of the backward land. The distance it would take would be the product of the speed of light and the time it needs to reach the eyeball of the president of the backward land. Now this distance can also be written in a different way and equated to that different way. The different way is the distance it would take for the light to reach the eyeball of the president of the backward land is the sum of half the distance between the two presidents. Remember, I told you the light bulb is in the middle of the table and the length of the table is d, as I mentioned earlier. The portion of the distance the light would have to travel pertaining to the president of the backward land would be half of d. And there is another portion that the light would have to travel, and it is as much as the distance the president of the backward land traveled while the light was moving through the distance of d by 2. So that distance that the president of the backward land had moved while the light was in transit is the product of the velocity of the train and the time it would take the light to reach the eyeball of the president of the backward land. So the section of the light beam near the president of the backward land would have to cover a certain distance, and that distance is expressed as two different expressions. Since the distance is same, these two expressions are equated. On the left hand side of the expression is the product of the speed of light and the time it would take for the light to reach the eyeball of the president of the backward land, and on the right hand side of the expression is a sum, and it is the sum of half the distance between the presidents, the length of the table, and the product of the velocity of the train and the time it took the light beam to reach the eyeball of the president of the backward land. So clearly in this equation we can see that in the left hand side there is a product, in the right hand side also there is a product, but there is also a sum, and the products in both the sides consist of a common term. That term is the time it took for the light beam to reach the eyeball of the president of the backward land. From the equation that has been made, one can find out that time by shifting all the terms of the required time on one side and the rest of the terms on the other side, that is the right hand side. The expression for the time it took for the light beam to reach the eyeball of the president of the backward land is a ratio of half the distance between both the presidents and the difference between two velocities, that is the velocity of light and the velocity of the train. If you were to perform the same math on the side of the president of the backward land, the distance the light beam travels is the product of the speed of light and the time it took for the light to reach the eyeball of the president of the forward land. And that product is same as difference of two distances. And what are those two distances? One is the distance the light beam would have to travel along half the length of the table. That is the distance between the bulb and the president of the forward land. But that distance is reduced because the president of the forward land is moving towards the light beam, and therefore we subtract the distance the president of the forward land had moved towards the light beam. Finding out the distance the light traveled along the length of the table is easy. It's half the length of the table. The distance the president of the forward land had traveled towards the light beam is again a product. The product of the velocity of the train is moving this way, and the time it took for the light beam to reach the eyeball of the president of the forward land, who is moving towards the light beam. By equating the product on one hand and the difference on the other, one would again get an equation that consists of two products, one product on the left hand side and another product on the right hand side. And the product on the right hand side is a part of a difference, and there's a common term between these two products, and that term is the time it took for the light beam to reach the eyeball of the president of the backward land. If one were to arrange the time terms on the left hand side and the rest of the terms on the right hand side, one can get the expression for that time, and that expression is the ratio of half the distance between the two presidents or the length of the table the same term that we got in the numerator of the expression for time with respect to the president of the backward land. I told you ratio, so the ratio of half d, and this time it is the sum of the speed of light and the velocity of the train. So if we were to compare the two times, the times the light took to reach the eyeball of the president of the backward land and that of the forward land, what is common is the numerator, that is half of d, but the denominator differs. In the former case, the denominator is a difference of two terms, whereas in the later case, the denominator is a sum of the same two terms. It is now natural to conclude that the time it took the light beam to reach the eyeball of the president of the backward land would be greater than it would have taken for it to reach the eyeball of the other president, because the denominator in the former case is lower than in the latter case. So clearly, through this mathematical expression, what we have concluded is it takes more time for the light to reach the eyeball of the president of the backward land than it does for it to reach the other president. And hence, the people outside the train observed that while the train was in motion, the president of the backward land had signed the peace treaty later than the president of the forward land. But I would like to turn your attention towards a particular point. In real life, if people were to observe the moving train and the signing of the peace treaty, the people outside the train would see it no different from the officials inside the train. The people outside the train would observe that both the presidents had signed the peace treaty simultaneously. While we derive that both the times are different, we should also keep in mind that the ratios that we compared, consisting of the denominators as a difference of two terms in one case and the sum of two terms in another, both these differences and sums consist of the velocity of light. And the velocity of light is 3 into 10 power 8 meters per second. If you compare that with the velocity of the train, which is the other term in the difference and the sum, the velocity of the train would be very, very small. Even if you were to take a worst possible case of 100 kilometers per hour, that is around 28 meters per second, and 28 meters per second is very, very small compared to 3 into 10 power 8 meters per second, the speed of light. So what I want to say is, the sum and the difference terms consisting of the speed of light and the velocity of the train would be almost same, which means we already know that the numerator, which is half the distance between the two presidents or the length of the table, for both the times is the same. So what we can conclude is, since the numerator and the denominator of both the expressions is the same, the times for the light to reach the president of the forward as well as the backward land will be same. So in real life, the people who are observing from outside the train would not see that the president of the backward land had signed the peace treaty later than the president of the forward land. But what I want to say in this discussion is, when the velocities approach the speed of light or are comparable to the speed of light, there would be a difference in the experience of the people who are outside the train and the people inside the train, the officials. I hope with this talk you're able to understand what would happen if velocities of the objects reach the speed of light or comparable to the speed of light.